Okay, so here's some more transformation stuff, and we'll just kind of work our way through the problems. I don't think anything's really new in this so much. Okay, so the idea here is we're going to start with point 3,5. A is 3,5. And then we're going to do all these different steps, different types of transformations to it, and we're supposed to end up with the point -10,1 at the end of it. So let's see. First, we're going to reflect it around the y-axis, around the x-axis. So remember, if you're going to reflect a point across the x-axis, then the x value stays the same, but the y value changes sign. So like if this was xy, this point down here becomes negative x. Oh, sorry, that's not right. It becomes x negative y because it's below now. So this point, whoops, sorry about that. This point becomes 3 negative 5. Okay, then we want to stretch vertically by a factor of 2. When you stretch something vertically, you take your point, right now we're here, and you stretch it out so it's twice as far. So that means that the y value gets doubled. So this is going to become 3 negative 10. Then we're going to move it 2 units to the right. Moving 2 units to the right means the x increases by 2. So we're going to get 5 negative 10. And we're going to rotate 90 degrees counterclockwise. So if you remember the 90 degrees counterclockwise rotation rule looks like this. You start with xy. When you rotate 90 degrees, it turns into negative yx. So the y was negative 10. This was our xy. And now the y becomes a negative, so it's negative 10, so positive 10, comma, and then the x gets switched. So some students get confused with that negative sign. Just think of it as you're switching the order of x and y and throwing a negative in front. So you're switching the order, so it becomes negative 10, 5, and then throwing another negative in front makes it positive. And then we're going to reflect it around the y-axis. So when you reflect across the y-axis, right, like that, the x values become, the y values stay the same, but the x value changes sign. So this is going to be negative 10. And then when you shift down 4, the y is decreased by 4. So that's how we get the negative 10, 1. Okay, so let's try the next thing. The next thing is to do the same exact transformations, but with a general point called AB instead. Not with 3, 5, but with AB. And so we'll do the same thing, but it'll look a little uglier, I'll say. So first we're going to reflect about the x-axis. So that means the y changes sign. So this becomes a negative b. Right? And that's exactly what we did up here. The y changed signs. Okay, then we're going to stretch vertically by 2, by a factor of 2. That means the y values, remember we doubled the y values here, from here to here. So we're going to double the y values to the next step. So it's a, and then negative 2b, because we doubled it. That's the vertical stretch by 2. Then we're going to move it 2 units to the right. When we move it 2 units to the right, up here, that was adding 2 to the x's. So it's going to be a plus 2. And then we didn't do anything to the y's. Then we're going to rotate 90 degrees. So remember, the 90-degree rule is this. We're going to switch the order of the coordinates and then throw a negative in front. So we're going to switch the order of the coordinates. We're going to throw a negative in front of the first one there, which makes it positive. Then when we reflect about the y-axis, oh, that's this. Then when we reflect, that sign in front becomes negative. When you flip over the y-axis, the x's change sign, so now it's negative 2b plus 2. Then we're going to go 4 units down. It's going to take the y value and subtract 4 from it. A plus 2, so it's a plus 2, and then down 4. So it's going to be a minus 2. So here's the final step right there. So the nice thing about this is that it takes any point you want, and if you plug it into this rule, then you get all these transformations done in one step. So like if we checked it, like if A is 3 and B is 5, like we had up here, if we apply this rule down here, so this is AB, then my answer should be negative 2B, so negative 2 times 5, negative 10. And then A minus 2 is 3 minus 2, which is 1. So you can kind of see how that would be useful if you had to do this a bunch of times. And in fact, we do. Because in part 3, it says, transform the triangle with B 6, 2, C 9, negative 2, and B 0, 4, using the same steps. Well, we already have a blueprint here. We know that AB is supposed to turn into negative 2B A minus 2. So that means 6, 2 is going to turn into the image point. So this is my little a, this is my little b. I'm going to get negative 2b, so negative 2 times 2, negative 4. And then a minus 2 is 6 minus 2, so that's 4. C prime become negative 2. The b here is negative 2, so that becomes negative 2 times negative 2 is positive 4. And then a minus 2 is 9 minus 2, so that's 7. And then d prime, let's see, it's going to be negative 2b, so negative 2 times 4, negative 8. Then a minus 2 is 0 minus 2, negative 2. So then here are the new points without having to do a ton of work. Right? Okay. Now in number 4, it says if you were to look at the sides of the original triangle, BCD, and you looked at its image from number 2, you could show the side lengths aren't in proportion with each other. So the triangles are not similar. So the question is, what messes up the similarity? So if we go back up here and look at what's going on. First, we got a point. We reflect it across the x-axis. So if I had some triangle and I reflect it across the x-axis, I'm not going to get the triangle. It's a mirror image. They're still congruent to each other. So that doesn't do anything. When I stretch it vertically by 2, though, that means that all these things get stretched out double. And you get a different looking triangle now. If you stretch it out just vertically, it gets taller but not wider. So that's kind of like looking at a, like if we took a circle and you only stretched it out vertically, you don't get a circle anymore, right? You get like this ellipse or something like that. So it's this vertical stretch that messes things up. You'd have to horizontally stretch by 2 for this to also work. So let's put that here. The stretch is only in the vertical direction. Have to, or also have to be in the horizontal direction with the same scale factor. To keep the shape similar. All right. Okay, let's look at the next part. Oh, let's see, number 5. Okay, so we got this triangle here, vertices labeled. Find the lengths of the 3 sides. So I'm going to do that by making some slope triangles, which hopefully you're getting used to by now. So here we go. Cross, up, cross, down, or up, I guess that way. Okay, so when I go up and down, the y's change. Negative 2 to 4 is 6 up. When I go across negative 4 to negative 2 is 2 across. When I go from -2 all the way to 10, that's 12 across. 4 to 0, going down is 4 down. Let's see, that'll have to be a 2, and this will have to be a 14. By the way, I'm using the fact that this thing's a rectangle to help me speed that up. Okay, so let's do some math to get the side lengths. These are all slope triangles, so they're all right triangles. So I can do 2 squared plus 6 squared equals DE squared. So that's going to be 4 plus 36, that's 40, equals DE squared. So root 40 is DE. Okay, I'll put that in here, root 40. Then let's see, what else? We've got 4 squared plus 12 squared equals EF squared. So that's 160 if you add all that together. And then you square root that, root 160. Yeah. So that's this one. And then the last one here, we've got 2 squared plus 14 squared equals DF squared. So that's 4 plus 196, that's 200. We'll square root that. And then I'm not going to bother simplifying because I don't have to really. Okay, so that's that. Here are the 3 side lengths. And then the next question is kind of a continuation. It says, find the side lengths of this triangle. So we'll do that. You might tell that they kind of look like they're going to be similar. And in fact, it says prove that they are. Okay, so let's see. This is going to be how far up? 3 up, 1 across. This is going to be -1 to 5 is 6 across. 1 to -1 is 2 down. This is 1 down, and this is 7 across. Okay, so 3 squared plus 1 squared equals RS squared. So 3 squared plus 1 squared is 10. And then we'll square root it. Okay. So that's root 10. Then we got 6 squared plus 2 squared equals ST squared. ST ends up being, let's see, that's 36 plus 4, so it'll be root 40. And then RT squared is going to be 1 squared plus 7 squared, which is 50. So RT is going to be root 50. Then it says prove that they're similar. So we have all the side lengths, so we can check if the sides stay in proportion. So if we do that, I've got, let's compare the 2 sets. So the shortest sides are the root 40 up here. Highlight these. So it's this one and this one. And I'll go blue for the root 160 is the medium side in that triangle, and the root 40 is the medium one in this triangle. And then we got the last ones right here. So let's see. It's going to be, where is the pen? There it is. So we'll go root 40. Check root 40 goes with root 10. And we're checking that the same as the blue side's matched up. So root 160 over root 40. Checking that the same as the green side's matched up. 200 over root. And when you have a root over a root, you can turn it into one big root. So this is going to be root 60. Is that the same thing as root 200 over 50? In each case, these turn into root 4, which are definitely equal to each other. So we can say, since the sides are all in proportion, triangle, what is it? DEF is similar to triangle RST because of SSS similarity. All three pairs of sides are in proportion. All right. Then the last part says, how can you transform DEF from step 5, from number 5, to get RST from number 6? Okay, so the sides here, the scale factor, a lot of students think that it's a multiplier of 4, or a division by 4. You'd have to shrink this by factor 4 to get to here, but you don't. It's a factor of root 4, right? So it's really 2. Right? So this one up here is twice as big as this one down here. So really what you're going to do is you're going to shrink by a factor of 2, or by a factor of a half, sorry. So first, shrink by factor 1/2, or contract is the, I guess, the more mathy term. And if you do that, then this point here, E is E prime, let's say, is going to turn into, if you shrink it by a half, it'll be -1, 2. And F prime is going to be 5, 0. I'm just cutting everything in half. And B prime is going to be -2, -1. So you get this triangle here, which is the right size now. It's half the size of the original, but it's not quite in the same location that we want. If you notice, the Y values are all off by 1. We have to actually drop the thing down 1 extra unit in order to get it in the right place. So then translate or shift down 1. Okay, I hope that helps some. And that's it. I'll see you guys soon.